Okay, picking up on the next one. F of x equals x, absolute value of x squared minus 1. Well, x squared minus 1, polynomial. Continuous for all reals. Absolute value. We just had that as a fact. Continuous for all reals. So x squared minus 1, the absolute value of x squared minus 1. Composition. Remember, composition is that idea of putting a function inside a function of two continuous functions. So continuous for all reals. Okay, so that's dealing with our basic facts. So the last thing we need to deal with, or the two things we need to deal with, the next one dealing piecewise defined functions. Just like when we did the limits, we did kind of all the normal things, and trig, which I know you guys don't necessarily consider normal, but then we also did piecewise defined functions. So dealing with piecewise defined functions here. So continuity and piecewise defined functions. To determine where a piecewise defined function is continuous, find first the intersection of the intervals where each branch is continuous. Next, using the definition of continuity, test the continuity status of each number involved in the function's restrictions. If the function fails to be continuous at a number involved in the restrictions, remove this number from the previously defined interval. Okay, so what on earth does that mean? Now, first of all, I've put more instructions down here than I really expect you to do. This is just part of the instructions I've listed there, is in case you share this with some of your friends who have a really picky math teacher. And if I hadn't put some of the stuff in there, picky math teachers might not like it. And that's this first fight. To determine the piecewise defined function is continuous, first find the intersection of the intervals where each branch is continuous. What I'm trying to say is that you should look at each one of these individual formulas and think about the discontinuities within those formulas and get rid of those first. You don't need to do that part. In this class, in my class, we are just going to concern ourselves with these numbers over in the restrictions and test these numbers. So the numbers in the restrictions are the only things you are going to have to concern yourself with. But in a greater mathematical scheme, someone could put something over here in the rules that you'd have to think about separately. I will not do that to you. All you're going to need to think about is the restriction numbers. So for this problem, we're going to start by saying that it'll be continuous everywhere except possibly at x equal -3 and 3. That's more of my part of saying that I'm not going to try to trip you up by having something other than those restrictions being questioned. That you can assume that it's going to be everything except possibly those numbers in question. Now, what we're going to do is use the definition of continuity, those three steps, to determine whether we have continuity at those numbers. So using the three conditions of continuity, f of a is defined. 2, the limit as x goes to a of f of x exists. 3, the limit as x goes to a of f of x equals f of a. Using those three conditions, test each of x equal -3 and x equal 3. So doing that, for x equal -3, 1, is f of negative 3 defined? So you just go up there and look at it. F of negative 3 equals e to the negative 3. And so condition 1 is satisfied. So I'm going to go on to number 2. But right there, that's that middle branch. If x is equal to negative 3, we use e to the x. 2 is the limit as x approaches negative 3 of f of x. Or does, I should have there. Does. That does not look like the word does. Exist. So going on to a new piece of paper here. Let's do the limit. So my thumb's going to copy down the function again. So let's recall that the function is f of x equals x minus 3 over x squared minus 9. If x is not equal to plus or minus 3, it's equal to e to the x. If x equals negative 3, and 1 over x plus 3 if x equals 3. So now when I do the limit as x approaches negative 3 of f of x, remember what this means. Close to negative 3, but not equal to negative 3. So this becomes the limit as x approaches negative 3 of x minus 3 over x squared minus 9. That I pick that top branch. Substitution first. That's going to give me negative 3 minus 3 over negative 3 squared minus 9, which is negative 6 over 0, which is undefined. Now, we haven't quite yet talked about those limits, and we'll talk much more about them in detail in the next section, but not too hard to say. I didn't get a number. This is not a number. And so the limit as x approaches negative 3 of f of x does not exist, and condition 2 fails. Condition 2 is there needs to be a limit. There's not a limit, so it has failed, and so we are not, f of x is not continuous at x equal negative 3. And there's no reason to go on to condition 3. We have decided that it's not continuous. So let's go on to condition or testing. So that was testing x equal negative 3. Let's test x equal 3. And we're already at 9 minutes, so we will conclude this video and start with the next video at testing x equal 3.